My name is Mania Gopadi, and I'm in the Systems and Networking group at CSAIL. The project that I'm getting into today focuses on optimizing reliability and utilization of internet-scale backbone networks. So the high-level idea is as follows. Let's say that there's a shared resource, like the internet, and a bunch of users, like you and your neighbors, who want to use this resource together. And so the goal of the network provider, say like Comcast, is to allocate this resource to these users optimally and fairly. And so usually this is often done by solving an optimization formulation with the objective of maximizing some notion of performance with a set of constraints. And so this method has been used for many years as the common technique to solve resource allocation problem in networking. But what I'm going to show you is that we can serve 3 times more users by taking failure probabilities into account. This number 3 times more users is significant because another way of thinking about it is that we can cut the cost by a factor of 3. The main lesson learned in our work is that probabilities are awesome, and we should take probabilities into account when allocating resources in networks like the internet. One way to think about it is that, say you're getting ready for a camping trip. You need to pack a lot of resources like water, food, tents, and you're also going to look into the weather conditions and road conditions. And if you have limited space in your car, depending on the road conditions, you will probably decide if you want to pack an extra spare tire or grab an extra energy drink. So we do take probabilities of failures into account. Failures in this case are these bad events that we don't want them to happen. And so it's very interesting that we haven't been taking them into account in networks as much as we should. And in particular, we have designed a system with probabilistic optimization functions for sending packets in an internet-scale network. Let me give you a concrete example to work through together. I'm going to talk about the traffic engineering problem in the internet. The traffic engineering problem is a classical networking challenge. It is a problem of configuring the allocation of traffic on network path with the goal of maximizing performance while efficiently utilizing the network resources to match the current demand. So it's basically a periodic process that runs every once in a while, say every 5 minutes. Traffic engineering has been the subject of extensive research in a broad variety of environments like ISPs, the internet, data centers, and whatnot. And in particular, we're going to focus on the internet-scale backbone. So let's say that we have 2 cities, Boston and New York, and there are 3 links connecting these 2 cities together. The capacity of each of these links is 10 gigabits per second, and let's say that we have a 10 gigabits per second traffic demand. And so the goal is to maximize this performance, and hence we're going to carry equal amount of traffic across these 3 links. And so the idea would be that we're going to carry, because we only have 10 gigabits per second demand, we're going to carry 10 over 3, 10 over 3, 10 over 3 across these 3 links. So this seems pretty simple, right? But it's not as simple when your network looks like this, looks like the entire world is connected together, and it costs $1 billion to build this network. So efficiency in this sense, which is dollar per gigabits per second, how much money am I spending to carry 1 gigabits per second of data from point A to point B, it becomes a very major metric. And so the traditional solution is to model network as a graph and then solve a linear program optimization function. Something like this. What I'm showing here is from a prior work paper. And so we can see that there's an objective function and there's a set of constraints about this. But things have evolved since 20 years ago. In particular, cloud providers are now interested in maximizing both utilization and availability of their networks. And so one way of thinking about it is that failures are one of the major aspects of the cloud infrastructure that can leave large impact on efficiency of the network. What does this mean? This means that link failures affect both utilization and availability of a network. Say you want to have a network with high utilization. This means that we're going to send a lot of traffic across network links, and hence when a failure happens, availability is low. And vice versa. If we want to have a network with very high availability, it means that we have to provision the network, over-provision the network, so that when failures happen, the availability is still high, which means that utilization is going to be low. And so traffic engineering under failure is a very important problem to solve. And today, the way we solve this is we optimize for the worst conceivable, but possibly unlikely failure scenarios. And the problem that this causes is that we excessively end up underutilizing the network to withstand shifts in traffic during failures. So back to our example, let's say we have Boston and New York with 3 links between them, and we would like to carry traffic between these two cities. We would also like to be robust with 2 simultaneous link failures. What this means is that if the top link fails and the middle link fails, we would like the entire traffic between Boston and New York to be carried over the bottom link. Since the capacity of this link is, in this example, 10 gigabits per second, it means that we end up carrying 10 gigabits per second of traffic when these 2 links have failed. But because we want to be robust against these 2 failures, we are going to carry 10 gigabits per second all the time, even when these links haven't failed. And this is where this underutilizing of the network comes to the picture. We end up sending 10 gigabits per second over 3 across all of these 3 links, which means that we are not utilizing this network in its capacity. Let me show you how this happens in practice. What I'm going to show you is on the x-axis is time, on the y-axis is normalized link utilization. And we are looking at the 2 links between Boston and New York. What happens is that everything seems normal except on August 4th. On August 4th, the top link has failed. And so its entire traffic goes down to 0, but the bottom link has enough capacity to capture the entire traffic, not only its own traffic, but also the traffic of the top link. And so the network continues to function as such. The interesting thing is, if you look at the traffic around the year, through the rest of the year, this is the only failure event that happened. And the bottom link is operating at roughly 25% of its utilization most of the time. And this is where we want to take advantage of this. By knowing the probability of these failure events, bad events, the question is, can we do better or not? And so our approach to traffic engineering under failures is to utilize the failure probabilities and to reason about the likelihood of different failure events. And we provide a mathematical probabilistic guarantee for availability of that network. So going back to our example, I'm going to add an extra bit of information. I'm going to tell you the failure probability of these 3 different links. So notice that the middle link has a slightly higher failure probability than the top and bottom link. So very simple. What I'm going to do is that I'm going to allocate 0 traffic to that middle link because its failure probability is pretty high, so I don't even want to carry any traffic on it. What this means is that I end up carrying 20 gigabits per second of traffic across this network most of the time, 99.8% of the time. And so given an uncertainty factor, given the failure probabilities of these different links, what we're looking for is a flow allocation vector, which is how do we divide traffic across these links to satisfy a given traffic demand. And so we would like to make a statement like this. For all the flows in this network, 90% of the demand is satisfied most of the time, say 95% of the time. I'm just going to flip this. For all of the flows, loss will be less than 10% of the demand most of the time, 95% of the time. And so the key idea in our approach is the following. Given a network, given the uncertainty of the different components of that network, this vector labeled by y, we would like to find the vector x, which is the allocation of the traffic, that maximizes the throughput all the time. The idea is that we're going to change this and we're going to solve this formulation to find this value x that minimizes the loss with a given probability, with some probability beta. And that's where we can serve more users while measuring the probability of failures. So how do we do this? Let's think about a given failure scenario. The key technique that we're using is a scenario-based formulation. Let's take a failure scenario. This failure scenario could be one link failure, or it could be a set of correlated link failures. Let's measure the loss associated with this failure scenario. This loss could be the amount of unsatisfied demand, packet loss, or an increase in latency. And let's measure the probability associated with this failure scenario. And if I put all the failure scenarios together in a graph, by having a target probability of, say, 0.95%, The area under the curve, when it hits 0.95%, finds a value at risk, where it means that the probability of loss is less than 10% in this example, with probability, the loss will be less than 10% with a given probability, in this case, beta equals 0.95. So we can write a mathematical formulation to find this point for us, and we can scale over multiple scenarios. But the question is, what about the worst case failure scenarios? What about these worst 5% of scenarios? Our formulation takes care of this by minimizing the expected loss of all the failure scenarios when their loss is larger than the value at risk. I won't go into the details of the formulation, but the system's architecture is as follows. We have a traffic engineering optimization function that takes the topology of a network into account, takes the demand of the network into account. It adds the failure probability of different scenarios into it. And given the target availability, let's say 0.99, 0.999, it puts them all together, it solves the optimization function, and it gives you a flow allocation. So to sum up, the idea is using probabilistic optimization to solve the problem of resource sharing. Let's say we have a shared resource, anything like a set of computers or a data center, roads on the globe, or office space. The key point is to define a failure scenario for this shared resource. Define the loss associated with these failure scenarios, and define the probabilities associated with these failure scenarios. And then you could leave the rest to our code base. And what we're going to do is that behind the scenes, we change the objective function into one that minimizes loss with a given probability that's an input to the problem. And then what this means is that after solving this optimization function, we can serve more users and hence reduce the cost by a factor of 3. So if you want to see this in action, head to our website and check out our demo, which allows you to run through some possible failure scenarios and observe the impact of different variables on the network. And feel free to contact me at gobadi@ccl.mit.edu.